some members like Shuram, Supurna, Raghu,
Uh,
they are invited the
uh,
members, it seems.
okay, fine, no problem. Let them join anyway. So we'll begin. So let me first of all formally welcome all of you to this meeting. I would like to welcome all the KPA members, students, and other invitees to this online program, which we have been conducting since 1.5 years, since October 2023, with the view of continually educating our members, especially teachers, on a variety of topics, because so many developments are taking place and our teachers should not fall behind. So we have been arranging these online programs, that is next best thing to personal programs, in-person programs, which we are not able to do. So we are very fortunate enough to have the cooperation of faculty members from colleges, universities, and institutes like ICTS. We are very grateful to them. And we've also conducted some lecture programs in Kannada also, regional language, in line with the NEP directives, because we have to encourage the usage of the local languages in higher education also, not just at the primary education, just for the sake of comprehension. The students who come from mostly from rural area, they find it very difficult to communicate in English. So to reduce burden is a good idea, but it takes a lot of time and effort to bring this sea change, that is the change of medium of instruction. Anyway, we should make a contribution to that effect, so which we are trying to do. So today we have a very distinguished professor from ICTS, Professor Joseph Samuel. So he will talk about relativity in navigation, an interesting topic, modern topics. So before I request him to speak, I'll just give you a brief introduction to his career. Most of you might be knowing him from his activities at RRI. So briefly, Professor Joseph Samuel completed his postgraduate degree from IIT Kanpur in 1977 with an integrated master's in physics. He acquired PhD from Indian Institute of Science in 1984. Professor Samuel joined Raman Research Institute as research faculty in 1982. He was associate professor during 1993 to 2001 and became professor in 2001. Since 2017, he is professor emeritus at RRI. He was a research associate at the University of Utah, Salt Lake City, visiting research assistant professor at Syracuse University, and visiting scientist at Harishchandra Research Institute, Allahabad. So he has a broad range of contributions in the scientific field he has made. So Samuel worked in several areas of theoretical physics, such as general relativity, classical mechanics, constraint systems, classical and quantum optics, statistical mechanics of soft matter and quantum information. His research has the unifying theme of differential geometry and topology in physics. He has worked on the Ashtaker formalism, which includes a covariant Lagrangian approach to the Ashtaker variables and the gravitational instantons derived from the gauge theory gravity analogy. Professor Samuel is interested in music, gardening, and literature. He has also interest in popularization of science. He has delivered talks to school and college students on subjects ranging across black holes, topology, cryptography, and magic squares. He has written several popular articles to take science to aspiring physics students. He was instrumental in setting up a theorist lab at the theory group of RRI, Raman Research Institute, which aims to kindle interest in physics in students. So we are very thankful to Professor Samuel for sparing his time and giving us the talk today on relativity and navigation. Over to you, Professor Samuel.
Thank you, Professor Kagali. I'm very happy to address this gathering. But before I start, let me just say a few words about in response to the remarks made by Professor Kagali. Yeah. You mentioned that you are interested in bringing higher education in the regional languages.
Exactly.
Yeah. So I would like to say that, well, one of the people who's attending this talk is my wife, Supurna, and her mother was the student of Satyan Bose.
Oh.
Satyen Bose was very, very strongly of the opinion that science should be taught in the regional languages, so that people understand that it's part of their world and not part of some foreign world.
Exactly, exactly.
So the science takes a deeper root if it's taught in the native language, right from the school to the college level. And he has also been responsible for translating many works into Bengali.
Oh,
Yeah, and actually, my mother was also
Influenced by that.
mother was also involved in
Meeting ಇದೆ.
popularizing science in
nice.
Bengali. Yeah,
No,
inspired
even
by S.N. Bose.
yeah, very nice.
S.N. Bose in turn was inspired by Tagore, actually, Rabindranath Tagore.
Yeah.
He had written a book called Vishwa Porichaya in Bengali, and that was also the motivation behind it, that
Very
bringing science to a wider audience, so that
even C.V. Raman had the same opinion. He said that we should really bring the educate in the local language only. And that's the best way of interaction between students and teachers. So we are facing that difficulty, the communication between the teachers and students. One of the problems is that the language problem. Anyway, please carry on.
Yeah. Okay. So let me say at the outset that I am not an expert on everything which is there in this talk. I have myself been learning about the subject as I go along. It's true that I have worked in relativity and I'm very interested in geometry. I've spent most of my life studying those topics. But I have not been familiar with navigation at all. In fact, I've gone sailing only once in my life. And the only navigation I've done is with the GPS. That's almost trivial to do these days. But instead of that, I'm trying to talk about the history of navigation using methods which are unfamiliar to many of us. So that's where I'm going to begin my talk.
Okay.
If you want to navigate in the city, you have to find your way around. The moment you leave home, you would like to go to various places and achieve your day's work. You use landmarks. In Bangalore, the standard landmarks, for example, are Majestic and the Silk Board or Dairy Circle. So you use these to find your way around the city. Now, this is all very well in the city, but you might be in a forest where you don't know the landmarks. You could be in a desert, and our military has been fighting in the desert recently, and they would definitely like to know where there are. There are no landmarks in the desert, and the only structures you can find are sand dunes. And sand dunes are notoriously shifting from one place to the other. So they are completely useless as landmarks. And the situation is even worse when you get into the open sea. The only thing you can see are waves, which are even more flighty than sand dunes. All you can see is the horizon and the sky. And you have to try to make the best of what you can see on the open sea in order to find out where you are. So the question that you're asking yourself always is, where on earth are you? Where on the planet are you located? Now, the question would be easy to answer if only the sky would stand still. If all the stars in the sky were standing still, you could just get a chart and mark the latitude and longitude of every star. That is, look at the star, take any star and see which point on the earth has that star directly overhead and mark its latitude and longitude. We all know that the latitude and longitude give us a coordinate system on the earth. And by specifying these two numbers, you can locate a point on the earth very accurately. In fact, sometimes you can locate it too accurately. Let me give an example of that. Recently, I had to get an e-kata for the house, for the house in which I'm staying. And the e-kata gives the latitude and longitude to about 10 or 15 decimal places. And I calculated and found out that they're evaluating the latitude and longitude to about the distance to about 1 angstrom. It's clearly an overkill. Most of the digits there are meaningless. But nevertheless, we would like to know where we are on the earth. And this is the most convenient system of coordinates that we use on the earth. So because the sky is not standing still, we cannot use the sky to locate ourselves on the earth. But there is one point of the sky which is constant. That point is the pole star, which is called Polaris. And you can think of Polaris as a sky mark. It's not a mark on the earth, it's a mark in the sky. So you can get some information from this star, which is called the Dhruv Tara in Indian culture. suppose you measure the angle between Dhruv Tara and the horizon. That will tell you the latitude. If you're in the North Pole, it will be directly overhead and your latitude is 90 degrees. And if you're on the equator, it will be on the horizon and your latitude will be 0 degrees. This works for the Northern Hemisphere. In the Southern Hemisphere, there's a constellation called the Southern Cross, which is quite close to the South Pole. And you can use the stars in the Southern Hemisphere to locate the South Pole, although there's no star there. And you can also use the angle of the noonday sun anywhere on Earth. Wait for the sun to reach its maximum height. And by measuring the altitude of the sun at noon, at the highest point, that will tell you the latitude. Yes, please. Yeah.
No, some cross-talking. Please continue.
Okay. Now, the longitude is much harder because of the rotation of the Earth. The sky is changing in longitude all the time as the Earth rotates. And it's a very important problem historically to find the longitude of a given place. The method that was used in ancient times is called dead reckoning. What they do is estimate the current position from the last known position. And then you try to estimate, for example, you throw some logs overboard tied to a piece of string, and the rate at which you're flowing, you're moving with respect to the water. By this method, you can get some idea of some estimate of the speed. But this is very inaccurate because the currents of the water and the winds are unknown. We can't really measure those accurately. So one strategy is that people used to stay close to the land, deep enough at sea to avoid the land, but use landmarks which are visible from where they are. There are dangers from rocks. Usually the region near the land is much shallower and you can hit a rock and sink. Also, when pirates know that you're close to the land, they can be on the lookout for you and attack your ship. There are other methods like sounding, where you measure the depth of the ocean. This is only possible when the ocean is not too deep. And you can either measure the depth by lowering a rope or by using echoes, which was a more recent technique. Another technique is to use the magnetic fields of the Earth. All these are very approximate. The people who understood this best before modern science were the Polynesians. They were able to spread across many islands thousands of miles apart by using very traditional methods of navigation, using the stars, using birds, using the currents, and a lot of observation. And we've lost all this very important knowledge, which they were able to achieve. And by this method of navigation, they were able to colonize many of the islands in Polynesia. Now, the ancient Greeks, there was this guy called Eratosthenes, who actually, in a different experiment, he measured the radius of the Earth to a very good approximation. He lived in Alexandria in the 3rd century before BC. So his argument was the following. If an astronomical event is visible from two locations, the difference in local time of the event will give you the longitude difference. So this observation connects time and longitude. For example, if there is a lunar eclipse or a supernova in the sky or some event which is at a fixed time, then at Alexandria, it might occur at 12 o'clock at midnight, let's say. And at another city, let's say Cairo, it might occur at a different time. And by keeping a record of these two times, you can measure the longitude difference between Alexandria and Cairo, and that gives you the longitude. But for this, you need to know the time at both places. Mm-hmm. So this is what connects navigation to relativity. In relativity, time is of the essence. Everything in the theory is a consequence of Einstein asking very deep questions about time. So you'll realize that the story of navigation and the story of relativity are intertwined with each other. And this intertwinement has enriched both fields. We have gained in navigation from relativity, and we've gained in relativity by the improvement of clocks because of the problem of navigation. Now, to know your longitude, you need a good clock. At the equator, the circumference of the Earth is 40,000 kilometers, and this distance is traversed by the Earth in 24 hours, one day. So in 1 hour, a point on the Earth is going to move by 1600 kilometers, or in 1 minute, 30 kilometers, or in 1 second, 460 meters. Now, if you can keep track of your time to the accuracy of 1 second, then you can solve the problem of navigation to the accuracy of about 500 meters. For example, I'm talking about the equator. In other parts, it will be slightly less in terms of distance. At the North Pole, there's no longitude at all. If you can locate yourself directly under the North Star, you know your location on the Earth without any error because you're at the North Pole. But of course, most ships don't go to the North Pole and very few people go there also. So let's leave out the 2 poles which are exceptional. Other places, you have a problem of finding your longitude, which reduces to finding the time at 2 locations. At your own location, you can look at the noonday sun and compute your local time. And if you have a good clock, you can locate the time, which is reading the Greenwich time, for example. You can find the time at Greenwich and then locate your longitude with respect to Greenwich, which is observatory in England. Now, this was a problem which was troubling all of the world, the problem of navigation. King Philip of Spain, the second, and also the third, offered a prize to anyone who could find a good way to determine longitude. Now, one way of doing this is to come up with good clocks. But let me also clarify that the motives of King Philip and the other kings of Europe who offered prizes was not entirely noble. They were interested, of course, in navigating the world for many reasons. One is for trade, the other is for colonization, to come into countries like India, which were very wealthy at the time, to either trade or to rob, whatever was more convenient, was more salubrious to them. So they were all interested in the longitude problem for this reason. And the problem now comes up of finding good clocks. And here there are 2 ways one can go. Good clock can be found in the sky. These will be called astronomical clocks. And one example of an astronomical clock is the moon itself. The moon is going around the Earth roughly once a month. From calculations, you can find out the position of the moon at different times at different places. And you can use that in order to find the time. For example, if you know that the path of the moon at Greenwich, where it would be, and you can make the suitable calculations and find out from an observation anywhere in the Earth what time it is in Greenwich. The only trouble with this is that the orbit of the moon in the sky was not completely understood. There were huge errors relating to the position of the moon, the angles of the moon. What you do is you measure the angle between the moon and some fixed star whose position you know in the sky. And by making readings of this kind, you can get a good idea, but it was not good enough because the error in longitude was about 2 or 3 degrees. Another clock in the sky were the moons of Jupiter. Galileo studied the moons of Jupiter and he realized that that gives another clock. And the moon goes behind Jupiter every 42.5 hours or so. That gives a regular clock. And all these are celestial clocks. They're up in the sky and they're unaffected by the motion of the ship. They're unaffected by any earthly event. They just go on ticking. The only trouble is that it's very hard to observe these things from a ship. Imagine trying to measure angles precisely from a ship which is rocking. And similarly, if you train a telescope on Jupiter, you need a telescope which is absolutely stable if you want to keep a tiny object like that in view. It's very difficult to take observations of Jupiter. There could be clouds in the sky. There's the difficulty of observing from a ship. And even more serious is that if the Earth and Jupiter are on opposite sides of the sun, you cannot really see Jupiter because the sun is so bright that Jupiter is only in the day sky and you cannot see it at all. So these methods only work for some part of the year. The other route is to look for clocks in the ship. And these are called chronometers. The only trouble is that these clocks have to be extremely accurate. They have to be unaffected by the rolling of the ship. And the ships are known to be in storms. And, it's very hard to keep time with the ship rattling around like a roller coaster. For example, if you take a grandfather's clock, the pendulum will go crazy if it's in a storm, and you will have no idea what the time is. Now, this was a challenge, and the challenge was, well, embodied in the prize, the longitude prize that was continued by Philip II. So one of the astronomers, a Danish astronomer called Ole Rømer, in 1676, he was observing the eclipse of Io, one of the moons of Jupiter. The duration of the eclipse is supposed to be about 42.5 hours. That is, the moon disappears behind Jupiter, goes all the way around, comes around, and disappears again. Those are two precise events, which, according to Newton's theory of planetary motion, applied to the planet of to the moon of Jupiter, it should be about 42.5 hours. But there was a variation in the duration of this eclipse. He kept on taking observations, and he used a very good clock, which was designed by Christian Huygens. He found that the duration of the eclipse was longer when the Earth was moving away from Jupiter and shorter when the Earth was moving towards Jupiter. The maximum difference in the period of the eclipse was about 13 seconds, but it used to vary continuously throughout the year. Huygens had great confidence in his clock, which was designed by Huygens because he had tested it and found that it was extremely accurate. And also he had great confidence in Newton's laws of planetary motion. So looking for a way out of the dilemma, he attributed the delay in the eclipses to the finite speed of light. So between eclipses, if the Earth is moving towards the sun, the light has less distance to travel before the next eclipse. And you'll find that the period of the eclipse has been shortened by a small amount. So by using this theory, he concluded that the speed of light is actually finite. People had suspected this before, but this is definite proof that the speed of light is finite. And he calculated that the Earth-Sun distance is about 8 light minutes, which is the current value that we have. Actually, it was not he who calculated. Let me tell you the story in detail later. Now, you can see from this that the problem of navigation has led to a better understanding of light. The speed of light is actually finite, and this was first discovered by Rømer. Now, relativity depends entirely on the speed of light being finite. So putting together the finiteness of speed of light and the importance of time measurements, we find that relativity and navigation are very closely intertwined with each other. The stories are inseparable. Now, that's the story I want to tell you today. Let me just say that I made a long introduction, so I want everybody to understand the general part of the talk. And later I will be going a little bit faster, but yeah, that'll be, yeah.
I don't know where.
I'm sorry?
No, please carry on. Some cross-talking.
Okay. Now, another part of the story is something that happened in Britain. Britain's greatest maritime disaster happened in 1907. 2,000 sailors died while they were returning home from a naval battle at that time. And what happened is that on the way home, they were hit by some storms, and they were using dead reckoning to find their way home. And when there's a storm, everybody loses control of everything. And they had no idea where they were. They thought they were closer to home than they were. They were actually quite far away, and they ran into some rocks on the island of Scilly, which is a place just off the coast of England. And all these sailors died. And this led to a huge debate in England about finding the longitude. And that led to the installation of a longitude prize in England in 1714. They were offering a princely sum of 20,000 British pounds to anybody who could come up with a method of finding the longitude to 1 degree or less. Of course, the lunar distance method was at 3 degrees, and they were also trying to do this. But there was a brilliant man called Harrison. He was a carpenter and untrained in many things except carpentry, but he was a genius in some ways. He learned the art of clockmaking, not in response to the prize, but he was independently interested in everything. And he was making clocks before the longitude prize was announced. And he made clocks that were better than any clock in existence at that time. Many of the clocks at that time would lose about 15 minutes in a day. And you had to routinely correct the time at noon when the sun was up in the sky. His first clock, H1, lost only 1 second in a month. That is very good for clocks at the time. Now, he was actually a perfectionist. It was one of his faults. And maybe I should cut the story short, but let me just tell you very briefly. What he did was to produce 5 different clocks, and all with ingenious methods of making them more and more accurate. For example, expansion of metals was one of the problems. He designed a clock with using wood that was H1. Wood did not have the problem of expansion. Another problem was that many of the metal clocks, the parts needed lubrication. In bad weather, in cold weather, the oil would freeze up, and then that would cause a lot of friction and change the ticking of the clock. And one of the clocks that he had designed, he used a wood from Africa, which had some intrinsic oil inside the wood. So you didn't need to lubricate it. The oil was the clock was naturally self-lubricating, and nothing used to happen to this. The oil would be released at the time that it was required by the wood. And all these achievements of his were unfortunately in vain. What happened is that the prize was to be decided by a council from the Royal Astronomy, from the Royal Society. And initially, they were all very, very honest and very forthcoming. They encouraged his efforts. But he was taking so much time to improve and perfect his clocks that many of the people in the original committee passed away. And then they were replaced by new people who had their own interest. They wanted an astronomical clock rather than a chronometer, a ship clock. And then they used to find some reasons for not giving him money and for impeding his work. And finally, he appealed to the king, who overruled everything and gave him most of the money which he should have got at a young age of 40. He got it at the age of 80, about 3 years before he passed away at the age of 83. It's an unfortunate story of a genius who's been neglected, a rustic genius who had powers of abstraction as well as making very concrete devices that would run with great precision. Now, this story was improved on later by Lord Kelvin. With the understanding of atomic physics in the 1890s, Lord Kelvin realized that the frequencies of atomic spectra could be used as frequency standards. Actually, a clock can be viewed as simply a frequency standard. For example, a tuning fork which you use for tuning your instruments, that is a frequency standard. It vibrates maybe about 300 times a second, and that gives you a clock, a regular motion of some system. Similarly, the atom does not suffer from the problems of friction or lubrication. And these days, the best clocks in the world are cesium clocks. And this has been perfected over many years. Now we have clocks which are stable to 1 part in 17 in the laboratory. But of course, there are other clocks which are not as good as that, which are sufficient for the problem of navigation. And in a parallel development, Michelson and Morley showed in their quest to find the motion of the Earth relative to the ether that the speed of light is the same in all inertial frames. And they were able to, this led to the theory of Einstein's theory of relativity, where his main contribution was to eliminate the ether entirely from the thinking. Maybe this is a good point for me to pause in case there are any students with questions or. Okay, if there are no questions, we learn about the world around us through light. Light travels at a finite speed of 3 × 10⁵ kilometers a second. This is a very large speed in everyday terms, and it's practically infinite from an everyday point of view. Newtonian mechanics does not have a role for this speed, and it was implicit that signals can be sent at any speed. First evidence for finiteness came from astronomy, that is Ole Romer in 1975-76. The eclipses of Io, the moon of Jupiter.
One comment, if you don't mind, one comment.
Yes, please.
Michelson-Morley experiment, they were doing that on the surface of the Earth. But definitely surface of the Earth is not an inertial frame. So in a sense, they had discovered the velocity of light being constant in all frames, not just inertial. Would you agree with that?
No, because in a rotating frame, yeah. See, if you go to an okay, we'll come back to this point when I'm talking about general relativity. Yeah.
Okay, please go on.
Yeah. So that's right. So Michelson-Morley experiment is done in one laboratory, which is in a state of motion with respect to the ether, right? So if you work inside the laboratory, it's true, it's a rotating frame, and there are effects, but the experiment itself can be done. Okay, we'll return to this point later, please. Yeah.
Okay.
Yeah. So
Speed of light.
okay, yeah. So the moon of Jupiter. So in fact, initially Romer had calculated that light takes 11 minutes to traverse the Earth-Sun distance. There was a slight error in his estimate. And the head of the observatory, whose name was Cassini, he initially did not believe that light travels at finite speed. But then he studied Romer's work, and he was convinced after studying it that it was accurate. And he improved on the observations with Romer's help over a period of time. He's the one, together with Romer, they came up with the better figure of 8 light minutes being the distance from the Earth to the Sun. And the finiteness of the speed of light led many years later to the theory of relativity. Now, the main message of relativity is that space and time are one. It's the same substance. Time and space are not different from each other. We must think of the world in a four-dimensional sense. Now, the first objection that you might have to this claim is that space and time have got different dimensions. Rulers measure meters. I mean, space is measured in meters and clocks are measured in seconds. Time is measured in seconds. However, this objection is removed by noticing that the speed of light is a fundamental constant. And this fundamental constant, c, can be used to convert space into time and time into space. So we will only use clocks. We will abandon any mention of rulers. And this led, in Einstein's hands, to theories of special as well as general relativity, which gives us a very good understanding of space-time and gravity. Now, here is a small introduction to special relativity, and this is mainly for students who may be in the audience. Now, suppose we put time on the y-axis and space on the x-axis, and I want to find out the time I would assign to this distance. I have a clock in my frame. This is observer A who's traveling vertically upwards, and I send a signal at t1. It reaches this point, and it's reflected back by an observer there, and it's reflected back to t2. Now, the time I would assign to this event, because light takes as long to go this way as it takes to come back, is the average of the two times, t1 and t2. That would be some point here. And secondly, if I want to know the location of this point, I'll take the total light travel time, t2 minus t1a, and divide it by 2, because in that time it's gone there and come back. So by these methods, I can give coordinates to any time here. So I will think of this point here as being at the same time as the midpoint of these two. That is some point here. So this point is said to be synchronous with that. Okay. Now, if there are two observers, A and B, and then I can do the same experiment, and I'll find because of the Doppler shift, we will see that there's a Doppler shift of T1, and you'll find that as he's moving away from A, that the intervals are stretched out. We're assuming that they synchronize their watches when they're at the origin, when they're both at the origin. You find that these two equations relate T1A and T1B, and this opposite equation relates T2A and T2B. It's opposite because T2 is receiving the signals from A is receiving the signals from B, and there's a Doppler shift in the opposite direction. You can put all these two together and concoct a dictionary between the observers A and B, and that is what gives rise to the Lorentz transformation. This is the Lorentz transformation written in some different coordinates, which I call x minus and x plus, which are basically linear combinations of the time and space. And this Lorentz transformations preserves the quantity t squared minus x squared upon c squared, which in relativity we call the interval. Now, if there are three observers, you can check easily that the Doppler shift will multiply. The Doppler shift from A to B multiplied by the Doppler shift from B to C will give you the Doppler shift from A to C. And that tells you that if I take the logarithm of the Doppler shift, I'll get the rapidity, which is an additive quantity, just as velocity is additive in Newtonian relativity. Now, the consequences of this are huge. One is that elapsed time is a path function. the time depends on the path taken by a clock. This is one of the most important consequences of special relativity. And this results in something called the twin paradox. If there are two twins who are born at the same time, and one of them stays at home and goes vertically upwards like this in the time as time passes, the other one goes far away, travels to the nearest star at speed very close to light and comes back. When they come back, the traveling twin will be younger than the twin who stayed at home. And that means that, well, the time elapsed actually depends on the path. It's not a function of the space-time event. It depends on the clock reading will depend on the path taken by the clock. Also, the notion of simultaneity is frame dependent. There's also a consequence of the special theory. Now, if you have two observers, you can synchronize the clocks as mentioned earlier. But now if you have three observers, A, B, and C, who are not in a straight line, you can synchronize A and B and then synchronize B and C. But you'll find that when you do that, A and C are not in synchrony, because if the three observers, even though all of them are inertial, if they're rotating, then there's a difference in arrival time between the clockwise ray and the anti-clockwise ray, and you'll find an effect, which is the Sciennes effect. So in the rotating frame of reference, we do not have special relativity. For example, if I take a fiber optic tube and send light clockwise and anti-clockwise, they'll come back at the same time if the tube is not rotating. But in a rotating frame of reference, the counter-rotating ray will come back before the co-rotating ray because the tube itself has moved. So this is the answer to the earlier question, that rotating frames, special relativity is not valid because of the impossibility because of the Sciennes effect. Yeah. So if you have three observers, you cannot synchronize clocks always. Yeah. So this led to a geometric view about space and time, which is due to Minkowski, and initially actually dismissed by Albert Einstein as being superfluous learnedness, but he slowly understood that Minkowski's geometric ideas are the way in which to introduce gravitation. Minkowskian geometry is very much like Euclidean geometry, except that there is a change of sign. And straight lines correspond to uniform motion. And in this geometry, time is a path function, and it's the longest distance between the endpoints of any line. It's not the shortest distance, which is there in Euclidean geometry. And we know that, for example, if I want to go to Indiranagar from where I am in Yelahanka, certainly the distance to Indiranagar varies depending on the path I take. I can take the shortest path, but that will go through many buildings. But I can take a longer path or an even longer path if I take an auto, which is trying to make more money. And in this geometry, parallel straight lines will never meet. Now, when you go to gravitational field, there's a simple experiment suggested by Hermann Bondi. By the way, the relativistic treatment I gave you was also due to Hermann Bondi. And this is a thought experiment due to Bondi. Suppose I have a set of buckets which are on pulleys like this. All the atoms, I keep cesium atoms in this bucket, and I keep cesium atoms in this bucket. The buckets here are all, the atoms here are all in excited states. The atoms on this side are all in ground states. So the energies of the atoms here are slightly higher than the energies of the atoms on the right. And because of E equal to mc squared, which comes from special relativity, the left side has got a larger weight than the right side. And as a result of that, the left side will keep on coming down, and you'll find that this is rotating. Now, you might think that what will happen is that the heavier atoms will come to the bottom and stay there. But as they pass the bottom, what I do is I use stimulated emission to tickle the atoms here and make them emit photons. One photon will make an atom emit two photons. One of those atoms is used to
excite them.
Yeah, that's right. One of the atoms is used to excite is sent up here and used to excite the atom on top. And the other atom is recycled for the next stimulation process. As a result of which, I would have constructed a perpetual motion machine. And this is clearly a paradox. So the paradox is a truth standing on its head to attract attention. So the truth here is that the photons which are sent from here to there will actually have a change of frequency. When they get up here, they will not be able to excite the atoms here because they've lost energy going from bottom to top. Just as the stone loses energy when you throw it up in a gravitational field. Going up in a gravitational field will actually cause the photon to be slightly redshifted. This is the gravitational redshift, and it follows just from this simple argument, or it also follows from the equivalence principle, which you can, well, that's a more familiar argument. So what this means is that clocks which are at a lower altitude, two cesium clocks, one down here and one up here. The clock up here will appear to run faster. If it looks at this clock, it will think that this clock is running slow. Actually, both clocks are running at the same rate if you bring them together. But if we separate them in height, the gravitational potential difference between the two clocks will tell you the amount by which the upper clock is running faster than the lower clock. So this directly proves that space-time is curved. Suppose I plot height on the x-axis now instead of time, and time on the y-axis. I have two ticks of a clock, a cesium clock. Let's say it's 1 unit of time here. It could be a second, for example. And then I'm measuring time in spatial units and light seconds. And then this is the path of a light ray emitted from here. And a path of a light ray emitted from here will be parallel to this one. But up here, I find that the length BC is slightly larger than the length AB. Now, this can never happen in an ordinary Euclidean geometry. A parallelogram has opposite sides of the same length, whereas this parallelogram has opposite sides of different lengths. So that proves that spacetime is curved. And this argument is due to Bondi to prove that spacetime must be curved. Now, in curved spacetime, you do something different. In Minkowski spacetime, we have a set of coordinates with a geometry determined by this expression, which tells you the interval or distance, the relativistic distance between any 2 points. This is called Lorentzian geometry. Straight lines are geodesics or extremal curves in this geometry. Now, if you have any curve, you can view it as consisting of many small pieces. Each is locally straight. And particles travel in straight lines which have a constant tangent vector, which can be either time-like or null. And you can see from the quantum correspondence between spatial coordinates and momentum that energy and momentum have also to be very much like time and space in their transformation law when you under Lorentz transformations. Now, Einstein was motivated by an interesting fact called the equivalence principle. It is an experimental fact that all bodies fall together in a gravitational field. That's because there is no difference between inertial mass and gravitational mass. So many people suspected that they could be different from each other. And Newton, Bessel, all the luminaries of physics did experiments. One class of experiments is to take a pendulum. And if the inertial mass, which is inertial mass, the movement of a pendulum is determined by two masses. One is the restoring force due to gravity, and the other is its resistance to inertia. It's a combination of these two masses that tells you the period of a pendulum. If these two are different, you'll find that the period of a pendulum will depend on the substance used. So wood, aluminum, and platinum might have different periods. It was looked for and not found. And finally, there were extremely sophisticated experiments which determined that equivalence principle was true to 1 part in 10 to the power of 15. So with an accuracy of 10 to the minus 15, all inertial masses are equal to all gravitational masses. So this means that in a freely falling frame, there is no gravity. Gravity can be eliminated. And I'm going to show you a simple experiment, and I want to thank my young friends from the Raman Institute Summer School. Those of you who are not familiar with special or general relativity can take a look at the lectures. It's in the RRI YouTube channel. It's called the Radio Astronomy Summer School, RASS. And both these theories are explained in more detail there. But here I'll just show you the experiment, which I did with the help of these students. So this is a Listerine bottle with 2 holes in it, filled with water. And we're going to drop it. The function of the towel is to catch the towel so it does not break. Catch the bottle so it doesn't break. Because I'm holding the bottle, gravity causes the water to stream out. When I drop the bottle, you'll find that immediately as the bottle is in free fall, the water stops streaming out.
Yes.
Yeah. So because of this, in a gravitational field, all bodies fall together. This experimental fact can be used to construct a theory of gravitation. You just locally eliminate the gravitational field by falling with it. An observer falling in a gravitational field can eliminate the effect of gravity and then use special relativity in that frame, in a small region of space. Since all bodies fall the same, we can think of the trajectories of the falling bodies as a property of the space-time and encode gravity to the space-time. So Einstein's great insight was to suggest that you can take the space-time interval and write it in this form and realize that gravity can be stored in the G mu nu coefficients, which are in this expression. X's are just coordinates. They do not have the dimensions or meaning of distance. They're like polar coordinates that we use in mathematics. But gravity resides in the metric and not in the polar coordinates. And space-time is flat only if G is a constant. And if G is a constant, you can pretend that space-time is flat. But even in a rotating frame of reference, you cannot do that. And there are effects of rotating frames that will actually affect us later on. We'll come to that later. So Einstein's key insight is that gravity can be encoded into the metric coefficients of space-time. So even in Minkowski space, you can use polar coordinates, and coordinates no longer have the meaning of distance. And if you go to a rotating frame, you find that light does not travel at constant speed, as I made that point earlier, because of something called the Sagnac effect. So I'll skip these 2 points. And does it mean that gravity is totally eliminated? No, it's only a uniform gravitational field that can be eliminated by falling. Non-uniform gravitational fields are real, and this is evidenced by the tides. If you live by the seaside, for example, people who are listening from Mangalore would have seen that the tide keeps coming up into the land and going down. These are caused by the gravitational field of the moon, and that is not uniform, and that's what causes the tides. So the tidal effects are real, and the effect of the moon on the water is very real. You cannot eliminate all gravitational fields, but you can eliminate a large good fraction of the gravitational field by just falling with it. Now, GR predicts a number of small effects in the solar system. One of them is that light bends in a gravitational field, which you can deduce qualitatively from the equivalence principle. It predicts that the perihelion of Mercury will advance. It's about 42 seconds per century. It tells you that that will happen, and it's been observed for many, many centuries before the principle of relativity. It also tells you that there's a gravitational redshift from the equivalence principle or from the argument I gave earlier. There are other effects like radar echo delay. All these have been verified to fantastic accuracy. The effects are very small in the solar system because the dimensionless number Gm upon c squared r, which is a measure of the importance of general relativistic effects, this is very small. It is 10 to the power of -9 for the Earth and 10 to the -7 for the Sun. So by falling with the Earth, we can eliminate this effect to a large extent. But this effect is still there, and that's what we'll talk about later. Now, in astrophysics, gravitational fields can be very, very strong. Eta can be of order 1. This happens in compact objects like neutron stars, pulsars, black holes, and also in the very early universe. General relativity is essential to understand these situations. And as I joked in the RNI summer school, if you want to do astrophysics these days without understanding general relativity, it's like wanting to be an accountant using the Roman numeral system instead of the Indian method of numbers with place notation and the value of 0. You just go crazy if you try to do GR, if you try to do astrophysics without knowing GR. The discovery of gravitational waves 10 years ago from black hole mergers has established the truth of the theory beyond any reasonable doubt. Now, I'll just dismiss all the stuff, which is very important, of course, but I want to focus on the effect of relativity on modern navigation with the global positioning system. And how am I doing on time?
Yeah, another 5-10 minutes.
Okay, I can finish in that time. Yeah.
10 minutes more.
Yeah. We now turn to the effect of relativity on modern navigation. with the global positioning system, we learned that we need some clocks in the sky in order to navigate effectively. Now, today, what we do is we put clocks in the sky. These are satellites. So in some ways, there's a compromise between the two systems. We have very accurate clocks, chronometers, in fact, but we don't put them in the ship. We put them in the sky. Yeah, so there's a compromise between the astronomical clocks and the ship clocks. They're not in the ship, they're in spaceships. And these are satellites which are orbiting the Earth. And their orbits are very accurately calculated and known. The GPS system, the global positioning system, has three components. There's a space component with 24 satellites which are orbiting the Earth in different orbits. And each satellite carries an atomic clock, a cesium clock, and the accuracy of this clock is about 1 part in 10 to the 13. That is, accuracy is 10 to the minus 13. The second component, after the space component, is the land-based control. There's a set of laboratories all around the Earth which monitor the clock, the signals coming from these satellites. And finally, there's the user, that is you and me, or a captain of a ship. You and me just wandering around town looking for movies or pizzas. We are one of the users. It could be a ship, a captain of a ship. It could be the pilot of an aircraft. All these people are interested in knowing their location. Where are they, on the Earth, or where are they in space? The satellites are continuously putting out radio signals with a space-time stamp. The space-time stamp gives a message, and the carrier signal is at 1575 megahertz. There are actually two signals. That's to correct for refraction effects, but conceptually one is enough. The space-time stamp tells you what was the location of the satellite when it put out the signal and the time. All calculations are done in a local inertial frame, which is freely falling with the Earth. When we freely fall with the Earth, we eliminate the effect of the sun's gravitational field, except for a very small and negligible tidal effect of the sun's gravitational field, and also the moon's gravitational field. All that gets eliminated to a large extent. The land-based control monitors the location of the satellites, computes their trajectories for the next few hours using general relativity as well as Newtonian mechanics with the general relativistic corrections, all calculated accurately, including the, whatever small effects are known to happen, so that their positions are accurately known. The user receives these timestamp signals and space-time stamp signals and calculates by solving this equation. This equation is valid in the local inertial frame. This equation has got unknowns t, x, y, z, the location and time of the user in that frame. And the data which is given is ti, xi, yi, zi, the location and time at which the satellite put out the signal. With these knowns and 4 unknowns and 4 equations, we can solve for t, x, y, z and find the coordinates of the user. And this calculation is done in the user's computer. T, x, y, z are the 4 coordinates of the user. With 4 satellites in view, he can solve for his location. This is the principle of the GPS. As I said, the actual system is more complicated. There are 24 satellites orbiting all over, but they're arranged in such a way that any user, almost everywhere on the Earth, will be able to make use of at least 4 satellites, sometimes more. But with 4, you can calculate in principle. And it's not just one signal, there are 2 signals. And sometimes when these 2 signals come at different frequencies, they might get refracted by a different amount. That can be used to also correct for the refraction. So it's good to have 2 frequencies to work with. The satellites are in orbit 26,000 kilometers from the center of the Earth. And the period of these orbits is half a sidereal day. A sidereal day is 24 minutes less than 24 hours. And this is the orbit of the period. The speeds of the satellites are about 4 kilometers per second. The power received on Earth is tiny. It's about 10 to the minus 14 watts per meter squared. But nevertheless, that's enough for us to get the information. But the fact that the power received is tiny makes the system vulnerable to jamming. For example, in wartime, it would be possible for the enemy to jam these signals. And if the enemy owns the satellites, they might even stop the signal from coming to you. All these things are possible. The important frames in this business, one is the frame of the Earth, because we want to navigate on Earth. If you're looking for a pizza or a movie theater, you'll be on the Earth. And you can use the Earth-centered Earth fixed frame, which is ECEF. Unfortunately, this is not an inertial frame, and light doesn't travel at the speed of light in this frame because of the Sagnac effect. This is the Earth-centered Earth fixed frame. And there's another frame, which is called the Earth-centered inertial frame. This is an inertial frame which was fixed to the Earth and falls with the Earth. And the direction of the z-axis was along the angular momentum of the Earth at that time. And the frame is also set to the Earth at that time and is freely falling with the Earth. So in this frame, light travels at the speed of light at c, and one can use these equations in that frame. There are relativistic effects which need correction. The special relativistic effects are the Doppler shift, the transverse Doppler shift, and the Sagnac effect in the rotating frame. All these effects have to be taken into account. And there's... Please repeat the question.
No. Some crosstalk. Please continue. Please continue.
Sorry.
There was some crosstalk. Don't worry.
Oh, okay. And in general relativity, we have to also correct for the gravitational redshift. The clocks which are up in the sky are in a lower gravitational potential than we are. So they will be ticking faster. Sometimes they do a factory setting so that the ticks exactly compensate for this effect. But you have to calculate the ticks from general relativity in order to know the effect. The first order Doppler shift is actually huge. It's 10 to the minus 5. Now, let me also say that if you want to know your location to 1 meter over the period of a day, you can calculate easily that the clocks must be accurate to 1 part in 10 to the power of 13. And the cesium clocks are accurate to this extent. But the Doppler shift is huge. It's 10 to the minus 5 instead of 10 to the minus 13. This has to be corrected for. Also, the second order Doppler shift is huge. It's much bigger than 10 to the minus 13. And the Sagnac effect also is 200 nanoseconds. That this formula for the Sagnac effect is the rotational frequency of the Earth times the area of the loop. If you take a tube and send light through it, the area of the tube divided by c squared multiplied by omega turns out to be about 200 nanoseconds. And that's a huge effect in terms of location. And the gravitational redshift is of dimensionally 10 to the minus 9. The relativistic effects definitely have to be calculated and allowed for. Otherwise, what you'll find is that your location will rapidly go out of, you will have no idea where you are within 1 day. Actually, even shorter than that. The ECI frame is inertial, and ignoring the Earth's gravity, this would be represented by the Minkowski metric. But if you include the Earth's gravity, you have a slight correction. This is a curved metric, which includes the curvature effects of Earth's gravity. And this is also not an inertial frame. I mean, this is not Minkowski space, but you can correct for all these effects. Where phi is a constant, is the Newtonian potential, and use the constant which is used to bring everything down to a particular geoid, that is a particular surface at mean sea level, where if you have clocks running there, they will be ticking at this rate. So the principle of the GPS is to use the constancy of the speed of light to convert space measurements into time measurements. Time measurement is the most accurate in physics. These days, all quantities are standardized to time units. Earlier, it was meters, kilograms, and seconds. And now everything is seconds. Meters are defined by just defining the speed of light and then converting that into meter. Similarly, more recently, in 2009, kilograms are also converted into time units. So the GPS is the realization of Einstein's view of the unity of space and time. The history of navigation is inextricably linked with the history of relativity. Better clocks, better understanding of space, time, and physics. Thank you.
Thank you very much. Now there is some time for questions. Do you mind? Would you take a few questions from the audience?
Of course.
There are some questions from YouTube Live.
You please ask. Okay, read out.
How was the ether medium maintained in the experiment?
Sorry, how was the
Ether medium maintained in the experiment?
ether medium.
Ether. There was no ether. Ether.
Yeah, there is no ether.
Okay.
So in relativity, we believe there's no ether. So we just ignore the ether completely. In which experiment? In the cesium clock or?
The audience not
Sir,
mentioned.
maybe they are asking about Michelson-Morley
Morley
experiment they conducted to find out whether the ether medium exists or not.
Yeah,
Maybe
yeah.
they are
So
asking on that.
that's right. So if there is an ether medium, it predicts that a motion of the Earth. Suppose you take the motion of the Earth through the ether, when it's going, if the ether is at rest, just like the air is at rest, if the Earth is moving through the ether in one direction, then you'll find that there's a delay difference in arrival time between light set transfers to the motion and along the motion. And the difference is about v squared by c squared. And they were looking for that difference as a fringe shift. And then they found that there was no fringe shift, which means that the special relativity predicts no fringe shift, which means that the ether does not exist. So the Michelson-Morley experiment basically proves that there is no ether, or rather it disproves the theory of ether. You can think of this experiment as an experiment with sound. Suppose you do the Michelson-Morley experiment not with light but with sound. You take a circular stage which is moving at some speed through the air, and you send sound signals this way and this way. You expect to find that there is a arrival time difference between the two beams, one which goes this way and one which goes the other way and comes back. And you can measure this with sound. I don't know anybody who's done the experiment. It will be very interesting to do this experiment and show that the air would actually give you a non-trivial Michelson-Morley effect if you do it with sound. So the thing about relativity is that light does not need a medium. It goes through free space, which was already clear from Maxwell's theory of electrodynamics, which is completely consistent with the special theory of relativity.
Okay, any other
And
question?
second question, sir. How curved space-time is implied from the principle of equivalence?
Yeah. So actually, the principle of equivalence only tells you that in the sufficiently small region of space, you can eliminate gravity. But the curved spacetime is implied by this Bondi experiment, which I told you about, with these atoms. Because from the thought experiment, you could conclude that the geometry cannot be flat. Because you could find a parallelogram in which the opposite sides had different lengths. That can only happen in curved space. Yeah. And let me take two, if that answers your question, let me take two of the questions in the chat. Srikanth asks, if you pressurize the bottle of liquid, will it behave the same way? My answer is yes. When you pressurize the bottle of liquid, even when you're holding it, there would be water coming out, right? Because there are holes in the bottle. So, but the moment you let it drop, if you, see, I was careful to keep the top of the bottle open. So the bottle cannot be pressurized. If you pressurize the bottle, you would and you close the top, then the water would come out at a higher speed. Now, that's why I removed the top. It's at atmospheric pressure. Now, the reason the water is coming is that the bottle is not falling with the water. The water wants to fall and it comes out of the bottle and falls. The moment I let go, the bottle and the water fall with the same rate, and there's no longer any need for the water to come out of the bottle. I hope that answers your question, Srikanth.
Yeah, he's not there, perhaps. Yeah. Next question.
Thank you, sir.
The next question is from Himadri. Yes, why do we use cesium atom only for the time measuring? Can we use other atoms? Yeah, actually, this is a very good question, and it's a technological reason more than anything else. The alkali atoms are easy to manipulate in the lab. The alkali atoms mean sodium, potassium, and all that. And the people who do this kind of experiments, some of my colleagues at the Raman Institute do these experiments, and the names are, there's the cold atom group at RRI. They do experiments of this kind. Sanjukta is one of them. And also there is Saptarishi. They manipulate atoms and they trap them and they cool them with lasers. All this kind of atomic physics is relatively easy to do with the alkali atoms. And they do a large number of experiments. In fact, some of the experiments done are not about timekeeping, And in fact, Supurna is involved in some of the experiments in this lab. She does the theory for the experiment. They try to measure the motion of these atoms in a very cold trap and study problems of statistical physics. And the reason for using cesium atoms as the standard is simply that it's technologically easier than using other atoms.
I have a simple question.
Yes, sir.
The kind of atomic clocks, that we see in textbooks and all that, they're very huge. But how can they be accommodated in satellites? That is my question. The atomic clocks that the satellites carry, are they different from what we see in the labs?
Yeah. The ones in the lab are of much higher quality. They can keep time to about 10 to the minus 17 accuracy. Yeah. So the ones up there are not as, don't have to be as accurate. And in fact, they talk of putting clocks on a chip. That kind of thing is also done at a much lower accuracy than the laboratory cesium clocks. So the laboratory clocks are actually used for multiple purposes, including VLBI, that is very long baseline interferometry, to have very good clocks there. So when you put clocks into space, you don't have the same luxury that you have in the lab, as you correctly point out. And so the clocks which are put up there are not as good as the clocks in the lab.
Smaller ones, sir. Very small ones.
Yeah.
Smaller
And
ones.
let me add to that. Can I add to the answer? In fact, the clocks in the user's hand need not be even as good as the atomic clocks in the satellites. That's because atomic clocks are not cesium clocks. I mean, the clocks in your mobile are not cesium clocks. They're crystal oscillators. And these oscillators are only good to the level of 10 to the minus 5. That is, they lose 1 second in a day. Right? I mean, actually, they're better than that also. I mean, but they're crystal oscillators, which are of very high accuracy, but they need not be as high as the clocks in the satellites.
Thank you.
Yeah.
So the effects of the gravitational fields due to other objects, sometimes there may be variations in the gravitational fields because sometimes some of the other planets come nearby. Anyway, some sun's gravity is definitely there.
Yes.
So all these things are also calculated. It's a many body problem, no? So
that's correct. So given the positions of all the planets and the sun,
yeah,
there is a gravitational force on Earth. Okay.
yeah,
That force can be eliminated by falling because of the equivalence principle. But there's a residual effect, which is the tidal force of the sun and the tidal force from the planets. These effects are there and they are calculated. They are much smaller than the current accuracy of the GPS.
Oh, okay. So they are much smaller. Okay.
Yeah. So they're neglected. So they're of the order of 10 to the minus 15.
Okay.
Whereas the satellite clocks of the order are of accuracy 10 to the minus 13. When we improve the accuracy of the satellite clocks by 2 orders of magnitude, then we have to take that also into account.
Yeah, because sometimes there's positions of the satellites are all coming on the same side. It can happen. No? So this kind of effects.
Right. And the effect of the sun is actually not very small at all. The sun effect is 10 to the minus 15.
Yes.
The tidal effect. So in fact, the tidal effect of the sun and the moon are comparable in size.
Yes. And similarly, the constancy of the velocity of light. Again, of course, I don't think the so-called density effects of the space may not matter here. I think it's much smaller. I think.
Yes, that's right. The local bodies are all been allowed for by just falling with the Earth. Whatever the center of the mass of the Earth is doing.
No, what I'm talking about is the so-called interstellar medium. I don't think the so-called velocities being different, maybe much smaller than again recognizable.
That's true. Yeah, that's certainly true. The interstellar medium has got about 1 atom per cc or something like that. Very small density.
Yes.
So Mallesh, you want to ask a question? Please ask.
Yes, sir. Professor Samuel, it was very interesting. Especially, your lecture is flooded with very witty remarks. And at 1 or 2 places you said you will cut the story short. So I would like to know whether you have written a detailed article on this, which you would like to see where the stories are told in detail. That is my first request. The second one is, a question which bothers me while teaching. in order to answer twin paradox, one uses sometimes they feel it can be explained within special theory of relativity, and some others say no, general relativity is needed. Kindly comment on this. Okay.
Yeah, very nice to hear from you, Malesh. Yeah, long time since we met. And I think probably in Mysore, I don't remember now. Okay,
Yeah.
yeah. So in answer to that, right now the only theory which seems to agree with the observations is Einstein's theory. There are always competing theories, and they should be. That's because we would like to see how good or bad Einstein's theory is in comparison to other theories. For example, there's the branch decay theory, which has got the metric as well as the scalar field, scalar tensor theory. And I think that, for example, the gravitational wave data would be quite different if you had a scalar branch decay theory. And there's also
some disturbance. Please carry on.
Okay, yeah. So can you come up with other? I mean, can you name some other theories which you are interested in?
No. Professor Samuel, my question was related to whether twin paradox can be explained within STR or do we need general relativity?
Okay. Actually, it can be done within STR also, and you can also do it within GR. You can take a very orthodox point of view and say in STR, I will only look at straight lines. Okay, then you will not permit the twins to go along curves. But you can go in a straight line from here to there and come back along a straight line. So all the acceleration happens only at the turning point.
No,
right?
but what you want to know is supposing the path is very long, then the curvature of space comes into picture. So GR effects have to be taken into account in explaining the twin paradox. That's what it means.
So I'm working in Minkowski space in a completely flat situation. Okay. And also, suppose I take the universe to be a closed sphere. Suppose the universe is a sphere, right? So I have one twin staying at home, right? And the other one going all the way around and coming back.
Yeah.
Right? So space is a circle, let me put it that way. A circle is flat, and space-time is a cylinder, right? So one twin stays at home, and the other one goes all the way around. Now, both are in inertial frames. Both are following straight lines, 0-6 of the cylinder. Only difference is one stays at home, the other one goes around and comes. But if I open out the cylinder, both are following straight lines. One is going like this and one is going like that along the diagonal, but they're ending at the same point. Even then I have a twin paradox. So I can formulate this paradox even in special relativity.
No, if the moving twin is going around, let's say a galaxy, then comes back, then what one has to include GR, isn't it?
No, let's take flat space. Then there are no galaxies or anything. Those have to take into account that gravitational field. I take flat space in the form of a cylinder.
Oh, that's all right, sir. In the flat space, supposing you consider the moving twin is going off so far away, orbits a galaxy and then comes back.
Yes.
Then one definitely has to take into account the GR effects, sir. That's what he means.
Yeah. So if I take a piece of paper, let me just, can I just switch off my screen sharing?
Yeah, sure.
Yeah. I'll take a piece of paper. Yeah. Wait. Yeah. Now I can see myself. So this is the cylinder. Can you see it clearly?
Yeah, we can see.
Yeah. So the vertical lines are the world line of the twin who's staying at home. Yeah. Now this space is flat. This space-time, it's a 1 plus 1D space-time. It's flat, right? This is an ordinary piece of paper, so it's flat. Now let me draw a straight line. From one corner to the other. That's clearly a geodesic because it's flat. Now what I'll do is I'll fold it down. Now this twin here has started from this corner and gone all the way like that and come here. The other twin has just gone vertically up like this. So this twin has been on a journey. The other twin has stayed at home. When they come back, this distance is different from that distance. So that's the twin paradox, even in a very flat space-time.
Okay.
Thank you. Very nice way of telling me. Thank you.
Srinath, Surya wants to ask a question. Srinath, please, you want to ask a question?
No, it's not my question. Just to supplement your previous question about the satellite clocks. One is cesium clock, another is rubidium clock. On the ground also nowadays, many space agencies are using maser clocks, which is of the order of more than picosecond order of accuracy. As the speaker was rightly mentioning, there will be drift in the clocks used in the spacecraft that will be corrected based on the ground clock time scales. Second point is about the size of the clocks, which you are telling in used in satellites is of order of maximum is 10 inch or 30 centimeter by 30 centimeter of the order also available. Except maser clock, which is there in ground, is of order of half meter by half meter by half meter. That's the cubical approximate size I'm saying. It is not very huge. India has also developed one atomic clock, which has flown in one of our IRNSS satellite. So there are clocks being developed in India. NPL, our Delhi Institute, is part of it. ISRO Space Application Center also is part of it. So there is quite a good amount of progress in what we call as a satellite clocks. This information I wanted to share.
Thank you. Yeah, no, it's absolutely essential to have all this technology developed in India within our control. So right now, in fact, many of the satellite GPS stuff is done in Colorado. That's the main laboratory. And there are laboratories around the world. And they, as you say, they take advantage of a large number of clocks, receive signal from them, land-based clocks. And then they take some kind of an average to come up with the maximum accuracy possible. Now, in peacetime, it's okay to use such things. But when in times of war, you have to be able to function independent of other agencies. So it's important for India to develop all these technologies, as we have been doing. ISRO has been at the forefront of many important developments in space. And everything you said is absolutely on point. We need to have technological capabilities to improve our, well, safety is one thing, and also a technology. And every kind of progress depends on our scientific attitude. And as you all know, our Indian Constitution actually mentions that one of the duties of an Indian citizen is to maintain a scientific temper and question everything that you see, and don't take it for granted just because it's being expressed in English, a foreign language to many of us.
Okay. I request now Professor Nagaraj, our General Secretary, to propose a vote of thanks. Nagaraj, propose a vote of thanks.
Yes, sir. In fact, you have started with longitude, latitude, and all those you have explained clearly, and how they are required for the navigation and other things. And especially when Mallesh asked the question about that twin paradox, you gave the example of that. It is fantastic. Thank you very much, sir. And the explanation is very, very nice. I hope that we could ask you again to give another lecture on this. I hope you would be able to do it. Thank you very much for your time and, of course, your talk from KPA, Karnataka Physics Association. Yes, sir.
Just 1 minute. If you will be available, we can arrange some in-person talks also in some colleges. That would be.
Yes, sir. Because the students will be available, especially the MSc and BSc students. If you talk to them, it will be very nice.
Yes.
Depending on our availability, I think maybe July onwards, the students will be available in the college. During that time, maybe August or September, we request you to come to the college through our KPA, Karnataka Physics Association. Thank you very much, sir. Thank you.
Thank you all for listening.
We also thank from KPA Jnanadhara, because Dr. M.K. Raghavendra is supporting this Zoom platform. And we thank even Professor Kagli. He keeps on conducting these programs almost every Sunday. And then, yes, Sai Venkatraman is going for that YouTube preparation. So, and KPA members. In addition to that, I saw some invited participants, Supurna, maybe, I don't know,
That's my wife.
She's
Yeah,
also
that's my.
from physics background.
Yes. She's also she's a physicist, and she's in the same house with me in 2 rooms away. But I gave her the link because I thought she also might be interested in following this talk.
Yes, sir. Very good, sir. So thank you one and all, and thank you all the invited participants. Thank you again, sir. Thank you. Thank you.
Thank you very much.
So we are now closing. Please join us for